You think the speed of light is just a number? 299,792,458 meters per second? It's a figure we've all seen in textbooks, usually presented as the ultimate gold medal in the cosmic Olympics. Fast, really fast. The fastest thing we know. Fine. But have you ever stopped to ask why? Why that specific number? Why can't you just add a bit more energy, build a slightly bigger engine, and push past it? Most people have never really thought about this. They just accept it because Einstein said so, the cosmic speed limit. But because Einstein said so is not an answer. That's just repeating words. When you really ask why nothing can go faster than light, when you dig into what is actually stopping you, you discover something so strange, so fundamentally different from your everyday experience, that it changes everything you think you know about space and time. In our daily lives, speed is a flexible thing. If you want to go faster in a car, you press the gas. If you want a baseball to travel faster, you throw it harder. We view speed as a property of the object itself, a measure of effort and kinetic energy. But the speed of light is different. It isn't just a speed. It's not just the velocity of a particularly quick particle. It is the structure of space-time itself. It is woven into the fabric of the universe in a way that makes the very concept of going faster literally meaningless. To understand this, we have to stop looking at light as a traveler and start looking at it as a boundary. Think of it like this. If you were looking at a map, you wouldn't ask why the North Pole is the northernmost limit. It's not because there's a wall there stopping you from going further north. It's because of the very geometry of the sphere you're standing on. Once you reach the pole, the direction north simply ceases to exist. The cosmic speed limit is the North Pole of our universe. It is the point where our traditional understanding of faster hits a geometric dead end. But before we can see that geometry, we have to understand how we found this wall in the first place. We have to look at the moment humanity first realized that the universe isn't instantaneous, that information has a pace, and that reality itself has a refresh rate. This realization didn't come from a laser or a spaceship. It started with a ball falling to the ground and a man who had enough confidence in the laws of nature to track the moons of a distant giant. This was the beginning of an avalanche of discoveries that would eventually collapse our traditional view of reality. To understand the speed of light, we first have to understand the gravity of our situation literally. Let's start with something simple. Things fall. If you drop a ball, it falls 16 feet in the first second. This is what Galileo measured, and for a long time it was just a localized fact of life on Earth. But then came Isaac Newton. Newton looked at the moon and asked a question that seemed insane at the time. Is the moon falling too? The moon stays up there, orbiting in a circle, because it's moving sideways fast enough that as it falls toward Earth, it keeps missing. It's in a state of continuous falling. Newton's brilliant insight was to wonder if the force pulling that ball to the ground was the exact same force holding the moon in its tracks. To prove it, he needed a bridge, a mathematical structure he called the inverse square law. Newton proposed that gravity gets weaker with the square of the distance. If you go twice as far away, gravity is 4 times weaker. The moon is about 60 times farther from the center of the Earth than we are. So, according to the inverse square law, gravity at the moon's distance should be 62, or 3,600 times weaker than it is here on the surface. Newton did the math. If you take that 16 feet, a ball falls on Earth, and divide it by 3,600, you get about 1/12th of an inch. When he calculated the actual curvature of the moon's orbit, he found it deviated from a straight line by exactly 1/12th of an inch every second. It was a perfect match. This wasn't just a lucky guess. It was the birth of a new kind of scientific confidence. This confidence changed everything. Newton had taken 2 completely independent facts, the fall of a rock and the orbit of a celestial body, and connected them through a single universal law. He used this same logic to explain why planets move in ellipses and why the tides rise and fall. He even explained why the tides happen twice a day. It's not just the moon pulling the water toward it, it's the moon pulling the water on the near side more than the Earth, and the Earth more than the water on the far side, stretching the ocean into 2 bulges, By establishing these laws, Newton gave scientists a yardstick for reality. He created a framework where, if the measurements didn't match the math, you didn't just assume the math was wrong. You assumed there was a hidden truth you hadn't discovered yet. This set the stage for an avalanche of discoveries. Because we had total confidence in the law of gravitation, we were finally equipped to notice when something was off in the heavens, and that discrepancy was exactly what led us to the first measurement of the speed of light. Once the law of gravitation was locked in, scientists began testing it with increasingly stringent measurements. The perfect laboratory was the Jovian system. By observing the moons of Jupiter specifically, Io astronomers could check if their orbits followed Newton's clockwork predictions. But as the measurements grew more precise, a massive problem emerged. The moons appeared to be breaking the rules. Sometimes Io would arrive at its predicted position 8 minutes ahead of schedule. Other times, it was 8 minutes behind. In the world of physics, 16 minutes of total discrepancy is a canyon. Many might have assumed Newton's laws were failing at such great distances, but a Danish astronomer named Ole Rømer had a different kind of confidence. He didn't believe the law was breaking. He believed something else was being overlooked. Rømer noticed a pattern. The moons were ahead of schedule when Jupiter was closest to Earth, and behind schedule when Jupiter was at its farthest point in its orbit. He realized that the moons weren't actually moving irregularly. Rather, the news of their position was taking time to reach us. This was a revolutionary moment. Before this, most scientists believed light was instantaneously propagated, that it existed everywhere at once the moment it was emitted. Rømer used the discrepancy in Jupiter's schedule to prove that light has a finite velocity. By calculating the difference in distance between Earth and Jupiter and dividing it by the time delay, he arrived at the first real measurement of the speed of light. Think about the weight of that. We didn't find the speed of light by measuring light directly. We found it because we had so much confidence in the law of gravitation that when the observations didn't match, we were forced to invent a new category of physics. We discovered a fundamental property of the universe because we refused to believe the universe was being inconsistent. This process illustrates the avalanche of discoveries that defines modern science. Each law we lock into place becomes a tool to pry open the next secret. If we hadn't trusted Newton, we would never have found the finite nature of light. And if we hadn't found that light has a specific, fixed speed, we never would have been forced to confront the fact that our common sense understanding of speed was a total illusion. The refresh rate of reality had been found, but the reason for that limit was still a mystery that would soon break our collective intuition. The discovery that light takes time to travel was the first crack in the dam of classical physics. It changed light from a magical, instantaneous presence into a physical thing, a messenger with a specific pace. But more importantly, it proved that the universe has a history. When you look at the stars, you aren't seeing the universe as it is now. You're seeing it as it was when the light began its journey. This realization triggered the beginning of a massive avalanche of discoveries that has continued for 400 years. Each new law became a lens. By understanding that light had a speed, we could start asking what that speed depended on. In the 1800s, James Clerk Maxwell discovered that light was an electromagnetic wave. His equations predicted that these waves should move at a very specific velocity, around 300,000 kilometers per second. But Maxwell's equations had a strange quirk. They didn't say what that speed was relative to. In everyday life, speed is always relative. If you're in a car going 60 miles per hour, you're moving at 60 miles per hour relative to the road, but 0 miles per hour relative to your seat. Scientists assumed light must be the same. They thought it must be moving through an invisible substance called the ether, and its speed would change depending on how Earth was moving through that ether. However, when they tried to measure this change, they found nothing. No matter which way the Earth moved, no matter how fast we went, the speed of light remained exactly the same. This was a crisis. It was as if you were running at full tilt toward a wave in the ocean, but the wave stayed the same distance away from you no matter how hard you ran. This is where the avalanche of discoveries hit a wall of pure intuition. We had the measurements, we had the confidence in the laws of electromagnetism, but the results made no sense. We were forced to choose. Either our understanding of addition was wrong, or the universe was hiding a secret about the very structure of space-time. It took a young patent clerk named Albert Einstein to realize that the problem wasn't with our measurements, it was with our definition of reality itself. He realized that for the speed of light to be constant, something else had to give. To understand why Einstein's solution was so radical, you have to let go of common sense. Let's make this concrete with a thought experiment. Imagine you're on a train, an incredibly fast one, moving at half the speed of light. You stand in the aisle and shine a flashlight forward. In your everyday world, speeds add up. If you throw a baseball at 50 miles per hour from a train moving at 50 miles per hour, a person standing on the ground sees the ball moving at 100 miles per hour. Simple addition, so logically, the person on the ground should see your light beam moving at the speed of light plus the speed of the train. But that is not what happens. The person on the ground measures the light and finds it's moving at exactly 299,792,458 meters per second. You, on the train, also measure it, moving at exactly 299,792,458 meters per second. No matter how fast the train goes, 90%, 99%, or 999% of the speed of light, the result is always the same. The speed of light does not add. It refuses to combine with your motion. This should break your brain. It contradicts the most basic logic of physical movement. If the speed stays the same for everyone, then the two pillars of speed, distance, and time must be the things that change. Speed is just distance divided by time, v equals d divided by t. If v, the speed of light, is a constant rate that cannot change, then d, space, and t, time, must be flexible. Einstein realized that the universe is not a rigid stage where things happen at a fixed pace. Instead, space and time are dynamic. They bend, stretch, and compress to ensure that the speed of light remains the same for every observer. This isn't just a math trick or an optical illusion. If you move fast enough, your clock literally ticks slower than the clock of someone standing still. The space in front of you literally shrinks. This is the price of admission for a universe with a cosmic speed limit. To keep the refresh rate of reality consistent for everyone, the universe sacrifices the constancy of time and the rigidity of space. We aren't just moving through space. We are moving through a structure of space-time that prioritizes the speed of information above everything else. If space and time are flexible, how exactly do they bend? To visualize this, you have to stop thinking of yourself as moving through space and time separately. Instead, think of a single, four-dimensional fabric, the structure of space-time. You are always moving through this fabric at one constant rate. Imagine you have a fixed amount of movement to spend. If you are sitting perfectly still in a chair, you aren't moving through space at all. Therefore, all of your movement is directed into the dimension of time. You are traveling into the future at the maximum possible rate, 1 second per second. This is why time feels normal to you when you are stationary. But the moment you start moving through space, you have to borrow some of that movement from the time dimension. You are diverting a portion of your total velocity through space-time away from time and into space. Consequently, you must move through time more slowly. The faster you go through space, the more your time speed drops. This is the space-time speedometer. If you could somehow accelerate to the speed of light, you would be using 100% of your available movement for space. You would have 0% left for time. At the speed of light, time literally stops. This is why a photon, which travels at this limit, does not experience time. From the perspective of a photon, it is emitted from a star and absorbed by your eye in the exact same instant, even if that star is a billion light years away. This trade-off is the reason for the cosmic speed limit. You cannot go faster than light because you cannot divert more than 100% of your motion into space. You cannot have less than zero movement through time. The speed of light is the point where you have completely run out of time to give. It is the geometric boundary of the structure of space-time, a wall built out of the very relationship between where and when. If the speed of light is a geometric limit, Why does it feel like a physical struggle to get there? In every science fiction movie, light speed is just a matter of having a better warp drive. But in the real world, the universe fights back. As you approach the limit, the very nature of your existence begins to change through a process called relativistic mass increase. Common sense tells us that the harder you push something, the faster it goes. But as you get closer to the speed of light, your energy stops going into increasing your velocity and starts going into increasing your inertia. You literally become heavier in terms of how hard it is to move you. To a stationary observer, an object traveling at 99.9%, the speed of light behaves as if it has enormous mass. This is where the math becomes absolute. To push an object with mass to exactly 100% the speed of light, you would need to overcome infinite inertia. To do that, you would need infinite energy. Since there is no such thing as infinite energy in our universe, no object with mass, not a proton, not a spaceship, not a grain of sand, can ever reach that wall. Light can travel at this speed only because photons are fundamentally different. They have zero mass. Because they have no mass, they have no inertia to overcome. In fact, photons have no choice. They are born moving at that speed and can never move at any other rate. They are the only entities that can live on the North Pole of the structure of space-time. For everything else, the universe has a built-in rejection system. It isn't an engineering problem. It's a hardware limitation of reality. You can get to 9,999% of the limit, but that final fraction of a percent is an infinite distance away in terms of energy. The cosmic speed limit is a lock that requires a key masslessness that we simply do not possess. This realization shifted physics from wondering how we could go faster to realizing that faster is a violation of the universe's internal logic. So, we've established that you can't go faster than light because you'd run out of time and need infinite energy. But there's still a deeper why that often frustrates people. Why is there a limit at all? Why isn't the universe just infinite? The answer lies in the fact that the speed of light isn't actually about light. It is the conversion factor of the universe. In our everyday experience, we measure space in meters and time in seconds. We treat them as different things, but in the structure of space-time, they are interchangeable. The speed of light is the exchange rate between them. It is the value that tells the universe how many meters are equivalent to 1 second. It's the constant that stitches the 3 dimensions of space to the 1 dimension of time. If you change the speed of light, you wouldn't just change how fast flashlights work. You would change the very geometry of reality. This speed is the maximum rate at which cause and effect can propagate. Think about that. It's the speed of happening. If an event occurs at point A, the news of that event, the physical influence of it, cannot reach point B any faster than the speed of light. If you could travel faster than light, you would be traveling faster than the propagation of causality. You would arrive at your destination before the cause of your journey even reached it. In the math of relativity, going faster than c is mathematically equivalent to moving backward in time. It would allow for effect to precede cause, which breaks the logical coherence of the universe. The cosmic speed limit exists to protect the sequence of logic itself. It ensures that the past stays in the past and that now moves forward at a rate that keeps the universe from collapsing into a chaotic soup of paradoxes. At this point, you might be tempted to think this is all just beautiful. Abstract mathematics, a clever way for physicists to balance their ledgers. But the structure of space-time isn't a theory. It is the hardware our reality runs on. We see the proof of the cosmic speed limit every single day, often in the very technology we hold in our hands. Take your phone's GPS, for example. The satellites providing your location are moving at about 14,000 kilometers per hour. According to Einstein's trade-off, because they are moving faster than you are on the ground, their clocks tick slightly slower by about 7 microseconds a day. Furthermore, because they are further away from Earth's mass, gravity is weaker, which actually makes their clocks tick faster by about 45 microseconds. If we didn't use the speed of light as a conversion factor to correct these clocks, the GPS on your phone would be off by 10 kilometers within a single day. The system would be useless. The fact that your blue dot on the map is accurate is living proof that time and space are bending exactly the way relativity predicts. We see it in nature too, with particles called muons. These are subatomic particles created in the upper atmosphere by cosmic rays. Muons are unstable. They should decay into other particles in about 2/millionths of a second. Even traveling near the speed of light, they shouldn't survive long enough to reach the ground. And yet, we detect them at sea level in massive quantities. Why? Because they are moving so close to the cosmic speed limit that time slows down for them. From our perspective, their internal clocks are lagging. They live longer because they are moving faster through space and slower through time. This isn't a trick of light, it is a physical reality. These particles are literally time traveling into the future because the structure of space-time demands it. Each muon that hits a detector on Earth is another piece of evidence in the avalanche of discoveries that confirms our common sense is wrong and Einstein was right. So, we return to our original question: why is the speed of light the limit? We now know it's because the universe isn't a collection of objects moving through an empty void. It is a unified structure of space-time, and light is the messenger that reveals its geometry. We don't hit a wall made of bricks. We hit a wall made of logic. You can't go faster than light because faster than light is a direction that doesn't exist in our four-dimensional reality. It would be like trying to walk south from the South Pole. This journey from Newton watching a moon fall to Rømer tracking a moon of Jupiter to Einstein reimagining the fabric of existence is the ultimate testament to the avalanche of discoveries. It shows that science isn't about collecting trivia. It's about finding the deep hidden threads that connect everything. The inverse square law that governs the tides is part of the same logic that requires GPS satellites to adjust their clocks, which is part of the same logic that prevents you from reaching the stars in a single human lifetime. The speed of light is the ultimate conversion factor. It is the speed at which now propagates through the universe. It is the maximum rate of cause and effect. It is the fundamental constant that ensures the universe remains a coherent story rather than a jumble of simultaneous events. Without this limit, the universe would have no structure, no sequence, and no history. We live in a universe that is far stranger and more beautiful than our ancestors ever imagined. It is a universe where time is a luxury you spend to move through space, where mass is a burden that grows with your ambition, and where the speed of a beam of light is the only thing that stays still while everything else shifts. The fact that we can understand this, that we can sit on a small blue planet and calculate the refresh rate of the cosmos, is the true beauty of physics. We haven't just found a limit, we've found the key to how the entire machine works. And the avalanche hasn't stopped. We are still sliding, still discovering, and still looking for the next truth hidden behind the light. Because in the end, science doesn't exist to give us comfort or to confirm our common sense. It exists to show us the truth, no matter how much it breaks our brains.